Okay, well, thank you for the opportunity to speak today. My predecessors in this session have done a good job of giving overviews from a federal government perspective with USGS and from a private sector perspective, particularly in terms of urban water use. And I will finish this up with a discussion on water availability and watershed management for agriculture, and particularly for irrigated agriculture, which uses the large majority of consumptive water use in the U.S. I think Jack showed a slide that showed where the demand was, and that demand pretty much follows where the reference evapotranspiration is in the United States. These areas in the Southwest and in the Great Plains, especially the southern Great Plains in Texas and Kansas and Oklahoma, and even up in southern Idaho, are places where traditionally irrigation has been the strongest in the United States. So we've been irrigating the part of the country that has the highest evaporative demand. Partly out of necessity, but also because in these areas we have ideal soils and climate for crop production. In the eastern states, we have plentiful rainfall, but not always good rainfall in the summertime, so we're subject to short-term flash droughts in the summertime that limit our yield potential to about 50% of the potential yield if we don't have irrigation. But if we do have irrigation, we can achieve 80% of potential yield, which is an economic factor that is driving irrigation to move eastward. Irrigated agriculture is important to the national economy. It provides 40% of U.S. crop market value on only 7.5% of the crop land. It does use 80% of the water that's used consumptively in the U.S., freshwater supplies, both surface and groundwater. It produces a very large economic impact and is a major source of export revenue for the nation. In the Plains states, irrigation produces 3 times the net revenue as dryland farming, and it doubles water use efficiency and stabilizes yields, which is why we see so much irrigation over the High Plains aquifer in the center of the country. But in the eastern states and the Midwest states, we've seen since 1998 some large increases in irrigated areas. This has got an economic factor rolled into it in that farming has become much more of a business enterprise in the last 60 or 70 years, and banks will no longer lend money easily unless there is some guarantee of year in and year out production. This slide shows that those trends, even since 1950, we've been losing irrigated land in the West, and we've been increasing irrigated land in the East, and since 1980 at about the same rate. So we really stabilized the irrigated area in the country. And you can see that in this slide. Since about 1994, the total irrigated area in the nation is stabilized at about 56 million acres. But since we started taking data, and when I say we, I mean the National Agricultural Statistics Service, we have seen increasing pressurization of irrigation corresponding with decreasing water applied. So we've seen technology come in a second blue revolution, the first blue revolution being the great expansion of irrigated area since 1900. The second blue revolution starting after World War II with increasing pressurization of irrigation, which makes irrigation much more efficient. Today we have about 65% of our irrigated area under pressurized systems. These are much more efficient than the gravity irrigation systems, surface irrigation systems that have declined to about 33%. And we've seen some large increases in subsurface drip, surface drip, and trickle systems that are often used for horticultural crops, which are the most efficient systems that we have for irrigation. Along the way, U.S. population has steadily increased, but total water withdrawals have stabilized, and water withdrawals for irrigation have declined steadily since about 1980, mostly due to technological changes in what is available in irrigation technology. ARS is a partner in the National Drought Resilience Partnership with USGS and several other federal agencies. And our part in that partnership is to provide research on effective water management, particularly in agriculture and watershed management. We do research on irrigation scheduling technologies for water use efficiency. We look at water productivity at multiple scales, water productivity being another way of saying water use efficiency. We look at irrigation application methods to see where we may apply more efficient methods of application and to which crops we might convert irrigation systems to more efficiently irrigate them. We're also working with drainage water management and control systems to provide technologies and to more efficiently control drainage water and to hold that water on the land where it can be used for sub-irrigation. And particularly in California, we're looking at the use of degraded and alternative water resources and what crops can be used efficiently to produce biomass from these water resources safely. And finally, we have a large watershed management program where we're looking at, amongst other things, how to reduce nitrogen and phosphorus pollution in our waterways through better watershed management. I'll spend some time talking about irrigation scheduling technologies for improving water use efficiency. We're doing a lot of work on sensor network-based irrigation management. At Bushland, Texas, Maricopa, Arizona, and Stoneville, Mississippi, we've developed wireless sensor networks to improve water use efficiency. And we do a lot of work with private companies through cooperative research and development agreements, CRADAs, often in conjunction with small business innovative research grants that those companies obtain, SBIR grants. Examples include a wireless infrared thermometer for detecting crop water stress, a patented soil water sensor that's used now by major agribusinesses and was only introduced last year. And we have a multi-location CRADA involving 4 ARS laboratories in the center of the country all the way to Florence, South Carolina for a patented site-specific irrigation scheduling, supervisory control, and data acquisition system that's being beta tested to most efficiently apply water where it's needed and when it's needed and not over-apply. Some applications in Fort Collins, we've got alternative canopy temperature methods for field crop irrigation management. And in Parlier, California, we've shown 50% post-harvest water savings in peach using infrared thermometers, which makes the commercial availability of an inexpensive wireless infrared thermometer a very good thing to have. And in Kimberly, Idaho, we've got now a new crop water stress index method, again based on infrared thermometry, for precise irrigation of wine grapes in the burgeoning wine industry in southern Idaho. Here's some examples of some low-cost, low-power wireless sensors and a center pivot irrigation system. It's being used in conjunction with these sensors that are integrated into the system to apply water variably in the field. And here's a couple examples of those systems, infrared thermometer and the True TDR sensor. We have systems now for site-specific irrigation management. And on the left, you can see a system in the field irrigating a cotton crop. On the right, you see a false color infrared image showing the lighter colors being a very warm canopy, the dark colors being a cool canopy, which is more irrigated, and the lower right showing that we can really strongly control using systems like this, both the water use efficiency and the yield of several different crops. We're also looking at remote sensing-based tools. We're working with NASA and the U.S. Navy to predict crop water requirements from satellite imagery. And I'll show a slide. This is affecting, or could affect, 10 million acres in California. That's the top system. We're at a couple of different labs improving that evaporation and transpiration partitioning that was talked about earlier, and showing that we can improve cotton water use efficiency with models that do that more effectively. We're also developing modeling tools at Maricopa, Arizona and Fort Collins, Colorado, integrating a dual KC method for ET simulation, crop water use simulation, and models that can be used for irrigation management. And in Florence, South Carolina, we're providing irrigation management guidance and proving out tools that farmers can use that will help them better manage irrigations of hay and flax. Here's an example. This is the California Central Valley. You can see Sacramento there, and all the blue areas are cropped areas. And when you're on this website, you can click on one of these cropped areas, and you can expand this image and get down to individual fields and click on them. And when you do, you'll get graphs, and this slide's a little old, so it only shows up to 2012, but you can get the crop cover, you can get the crop water use, it shows the crop type, and you can get the ET for the current day, in this case, a quarter of an inch, and this was a tree crop. And here's another example for another tree crop where the ET was about a third of an inch. It shows the crop coefficients, how they change over time, and a farmer can look at this and he can see how his crop is growing and using more water over time. When you have a crop coefficient of 1, for example, you're using the full reference ET. And a farmer can then manage irrigation over a growing season looking at this. Looking at water productivity at multiple scales, we've developed regional simulation models for crop water production functions that are influenced by soil, irrigation type, and irrigation and nitrogen fertilization levels that helps farmers choose crops that most efficiently use irrigation water and nitrogen. In Temple, Texas, we've developed a GeoAlmanac spatial forecasting model of crop productivity that's used with switchgrass, poplar, sugarcane, oilseed crops, all bioenergy crops, in conjunction with the U.S. Navy to enhance the Navy's fuel security. And in Fort Collins, Colorado, and Maricopa, Arizona, we've developed a ET model that's been improved to and able now to apply deficit irrigation scenarios, or be applied to deficit irrigation scenarios, which is a very new technology. We've not been able to adequately simulate deficit irrigations and provide information for decision making in the past. Here's an example of how the GeoAlmanac model is used. These are 3 different climate change scenarios. The top graphic on the right is the current day situation where biomass production for switchgrass is heaviest in the southeast, and the middle is a climate condition called B2, showing that there is some movement of switchgrass productivity towards the north. And the lower graphic on the right is the climate condition called A2 that shows that by 2080 to 2090, the switchgrass biomass production is heaviest up in the upper Midwest. This is all a function of CO2 concentration, soil type, and the water availability and what we expect that to be under climate change scenarios. Also in the remote sensing sphere, we've developed data fusion applications that take data from 4 different satellites, some of which only see a certain part of the Earth every 16 days, and some of which see it hourly. And we can fuse that data now to provide daily 30-meter resolution crop growth metrics, crop phenology, which is crop growth, the crop water use, and the crop stress, which is used for drought early warning. We can detect crop stress before the U.S. Drought Monitor shows that drought is actually occurring. We can see this early, as much as 2 to 3 weeks early. We've also developed a system for mapping daily and seasonal crop water use. The right graphic here is the Napa Valley of California, and this is now becoming available for daily irrigation scheduling in this wine country part of the Napa Valley, which is also growing some pretty heavy alfalfa, the darkest squares that you see there. We're looking at irrigation application methods to increase water use efficiency. The old irrigation application methods were pretty inefficient. Some of the new ones are quite much more efficient, but haven't been used with some of the crops that they could be used for. One of our new discoveries is that we can use center pivot irrigation for rice, particularly on coarse textured soils, but also on clay soils. And this really reduces the crop water use because rice is usually grown in paddies with standing water, and that water evaporates readily. But when we use center pivot irrigation, we can get a large reduction in water use and get the same yields, but really increase the water use efficiency. We're also showing that subsurface drip irrigation increases both yield and water use efficiency by reducing evaporation losses to the atmosphere, which keeps more water in the soil and available for plant growth and yield formation. And here's a slide showing center pivot irrigation of rice. I'll go past that. One of the new technologies that's becoming available from our center pivot manufacturers here in the U.S. is variable rate irrigation. And ARS is developing the decision support systems that are used to write the prescription maps. On the left, you see a prescription map for a variable rate irrigation system. And we're developing the decision support systems to better apply water variably around the field to match the crop water need. And in this research, we showed that we could increase the water use efficiency for corn by 27%, and the water use efficiency for soybean by 31% using this new technology, plus our decision support systems. We're also looking at drainage water management and control. In the Midwest part of the country, we have the paradox of too much water and short-term drought, often both in the same years. The too much water requires drainage, but the short-term drought requires supplemental irrigation. The economic consequences are driving some technological solutions that we are developing in conjunction with NRCS. What you see in the lower bar graphs are on the left the excess water indemnity payments, crop insurance payments, and on the right the drought indemnity payments over an 11-year period for 5 upper Midwest states. And the 5-year total for those is nearly the same. which is quite a paradox. But what it means is that we have to get the water off the ground when it's too wet so that we can plant, but then we have to be able to hold that water so the crop can use it once the crop starts growing. And here's one technological solution using, on the lower left, you see a gate that has different levels that we can set it at. We lower that gate to allow drainage water to flow off of the land in the spring. And on the right, you can see the fallow period where the water table is high. And then you see the water table dropping because we have opened the gates. We plant in March, in April, and then in May we close that gate and hold the water in the soil so the growing crop can root down and use that water. And when we do that, we keep the nitrogen and phosphorus that's in that drainage water on the land, and we reduce both nitrogen and phosphorus pollution in our waterways. And this is one solution, partial solution anyway, to the hypoxia problem. We're also looking at use of alternative irrigation water resources. In Parlier, California, for example, we're looking at drainage waters high in boron and selenium, and shown that they can be successfully used to cultivate mustard, opuntia, which is big cactus, and poplar, and produce added value selenium-enriched food products, which can be sold in parts of the world where selenium deficiency is a nutritional problem for large populations. The poplar is grown for biomass or for furniture lumber, and it helps lower high water tables that can be associated with salinity problems. In Riverside, we've developed a new regional scale salinity assessment tool based on salinity satellite imagery, and I'll show you a slide of that. And we've also developed a new crop water production function based on new models of unsaturated soil chemistry in saline water. In the upper left, you see a mathematical model and decision support systems that we've developed that allow us to provide irrigation guidelines for marginal quality water and crop yield projections based on that water quality and nitrogen fertilizer levels that can be applied to these salt-affected soils that you see in the upper right photo. Here's an example of mustard being grown with salty drainage water, and also poplar being grown with salty drainage water as well. The regional scale soil salinity mapping is a new product based on our unsaturated soil chemistry model. This was developed using 7 years of Landsat 7 CANIP response data and ground truth salinity data collected in 22 fields, about 600 hectare over the entire western San Joaquin Valley, using USGS and NASA data. And this is a graphic showing the soil salinity map of these farmlands, which has been ground truthed and shown to be very accurate. So this is very helpful for water managers and for individual farmers, and looking at the salinity status of their fields and where there are problems that are beginning to show up due to their irrigation habits or due to the non-availability of water, which is a severe problem in this current California drought. We've also worked with our partners in the Bureau of Reclamation and the Department of Interior, National Burn Area Emergency Response Teams, and also with NRCS by developing the AGUA automated GIS interface for watershed modeling that takes 3 ARS models and makes them very easy for people to use. So these have now been transferred, and this technology has been transferred to other national agencies and can rapidly predict the at-risk areas that can be focused on to target fire mitigation. And those areas that aren't high-risk areas, and doing so can result in multi-million-dollar savings. But what we're looking at here is how to model the water and the runoff in these burned areas and the erosion that would result from them. Nearing the end of this presentation, I want to talk about a joint effort with our lab at Boise, Idaho, and NASA JPL in California, and with the state of California, using the ice snowball model, which is an ARS snow model that is used with LIDAR data that NASA is acquiring. It's a basin scale airborne LIDAR data. And together, these can be used to map the snow density and greatly improve the predictions of eventual runoff during snowmelt throughout the Sierras. This was tested in the watershed for the reservoir that serves San Francisco and was very successful, and in this coming year will be expanded to cover the whole Sierra Nevada. We're also working with the Foreign Agricultural Service to develop a global root zone soil moisture monitoring model, where we take the soil moisture observing satellite data, which is a European Space Agency satellite, and assimilate that with the soil water balance model and provide a much improved projection of global root zone soil moisture, which is a very important indicator for crop yield around the world. And this doesn't just cover the southern part of Africa, but it covers the entire world, including the U.S., so it's very useful within the country as well. So thank you, and if there's any time for discussion, I'd be glad to have that.